By modern physics, the common question that comes to our mind is, why are we studying modern physics? After all, most of us want to become electrical engineers because that's the way the wind is blowing these days. तो हवा तो उसी तरफ चल रही है और हम भी उस हवा के रुख में बहना चाह रहे हैं, तो क्यों हम मॉडर्न फिजिक्स पढ़ना चाह रहे हैं और आपको क्यों एक लिहाज से नॉन फिजिक्स मेजर्स को क्यों इसमें एनरोल किया जाता है? उसकी वजह यह है कि मॉडर्न फिजिक्स इज नॉट जस्ट फिजिक्स, इट्स नॉट ऑल अबाउट फिजिक्स. मॉडर्न फिजिक्स इज one way to look at nature, and it's a very important way of looking at nature. Modern physics has transformed the way we understand nature, has transformed the way we invent technology. It has transformed our philosophical understandings of our surroundings. So it has transformed our outlook of life, and it's a very embracive concept. Embracive समझते हैं आप? It's a very wide concept. If you look at electronic circuits, almost 75% of all the revenue that comes these days in microelectronics comes from devices and inventions that are built upon concepts learned from quantum mechanics. Class का एक वक्त है, तो दो वक्त है. Please try to be on time on the class. तो अगर आप माइक्रो इलेक्ट्रॉनिक सर्किट्स की बात करें तो माइक्रो इलेक्ट्रॉनिक सर्किट्स क्वांटम मैकेनिक्स पे बिल्ड करते हैं. इवन दो you don't see the quantum mechanics at work, you don't see the quantum physics at work, but 75% of all the devices, of all the inventions that we are using today, ranging from Intel's microprocessors to your hard disks to your DVD ROMs, they are all built upon principles that are learned from the concepts that we will learn in this course. We talk about lasers. 2010 में लेजर की 50वीं सालगिरह थी. 1960 में पहला लेजर बना. ठीक, 2010 में 50 साल पूरे हो गए पहले लेजर के. तो अब लेजर्स हैं, आपकी डीवीडी रॉम्स में इस्तेमाल हो रही हैं, सीडी प्लेयर्स में इस्तेमाल हो रही हैं. लेजर कैसे काम करता है? सिलिकॉन क्या है? Almost 25% of the Earth's crust, जो जमीन का ऊपर वाली सतह है, उसका 25% is made up of silicon. Such an abundant material. But why is silicon so important in the electronics industry? What special features does silicon or germanium possess? What is the Big Bang experiment? What are X-rays? How does diagnostic radiology work? We have a fractured bone, we visit the hospital, and an X-ray is performed. How do solar cells work? So all of these are concepts that are vital for an understanding of today's technology and an understanding of nature itself, a fundamental understanding of nature itself. So there are two aspects to this course. One is a new way of looking at nature. नेचर को देखने का एक नया जाविया मिलेगा, नया अंदाज आपको मिलेगा, तो क्लासिकल फिजिक्स आपको नहीं है. आपने मैकेनिक्स का कोर्स लिया, आपने इलेक्ट्रिसिटी एंड मैग्नेटिज्म का कोर्स लिया फ्रेशमैन में, वो नेचर को देखने का एक क्लासिकल अंदाज है. एंड इट्स अ वेरी इंपॉर्टेंट पर्सपेक्टिव. विद दिस पर्सपेक्टिव यू कैन अंडरस्टैंड अ लार्ज पार्ट ऑफ नेचर. You can understand and decipher how a large number of inventions work. The Industrial Revolution was based upon mechanics and heat and thermodynamics. The entire communications revolution that emerged with the discovery or the invention of radio waves by Heinrich Hertz in 1890s, that uses concepts from electricity and magnetism. Every one of us carries a cell phone today. You need electricity and magnetism to understand how a cell phone works. Building new cell phones or optimizing cell phones. So the courses that you've studied will give you the basics of a large number of devices and concepts in nature. But there are certain gaps. The classical picture that was given to you in the first year is not complete. जब मैं ये कहूँ कि वो incomplete है, इसका ये मतलब नहीं कि वो powerful नहीं है. जो classical picture आपको मिली, it's very powerful because it explains a huge variety of ideas and concepts in nature, but it's not complete. उसके अंदर कुछ gaps हैं, या कुछ ऐसी चीजें हैं जो हम explain नहीं कर पाते. और अब जब हम मॉडर्न फिजिक्स पढ़ेंगे तो ये आपका इट इज अ फर्स्ट कर्टन रेजर, ये आपका पहला तारुफ होगा नॉन क्लासिकल फिजिक्स से. और नॉन क्लासिकल फिजिक्स के अंदर क्लासिकल फिजिक्स मौजूद है. अगर मैं एक डायग्राम बनाने की कोशिश करूं, kind of diagram that emerges. Unfortunately, the roof for this is broken, so I have to hold this. So what we've learned in the first year is classical physics. There's more to be learned. You haven't learned heat and thermodynamics, but still you've learned a good deal of classical physics. Now we enter the realm of non-classical physics, which is basically quantum mechanics or quantum physics. This word quantum, we will use this word almost 100 times every lecture, because this is what we're going to study. Now this quantum physics or non-classical physics is a superset of classical physics. When you look at classical physics, you're actually looking at average non-classical behavior. So what is really happening is you have this non-classical realm and you're averaging the non-classical behavior to observe what is called classical physics. And when you really want to look at non-classical physics, you have to do something special. Now a microprocessor, let me give you an example. A microprocessor works with millions and zillions and trillions of electrons at a time. ठीक है? उसके अंदर जब एक ट्रांजिस्टर स्विच ऑन या ऑफ हो रहा है तो उसकी प्लेट पे millions and billions and trillions of electrons are being stored. That is what generates a potential difference of that plate with ground. So you're looking at a large number of electrons. But suppose you perform experiments such that you do not have a large number of electrons. Say you have 10 electrons, 9 electrons, 6 electrons, or maybe a single electron. Now in order to explain that single electron, classical mechanics breaks down. न्यूटन की जो मैकेनिक्स है उसकी हद से आगे निकल गए आप. Isaac Newton cannot explain the behavior of a single electron. Isaac Newton cannot explain the behavior of a single photon, or say 10 electrons, or 7 electrons. So generally, when we are looking, as a rule of thumb, generally when we are looking at a smaller number of particles, say 1 particle, 1 electron, 10 electrons, 5 electrons, a smaller number of neutrons, a smaller number of photons, a smaller number of molecules, looking at an individual molecule, an individual hydrogen molecule, an individual methane molecule, or 10 methane molecules. Generally in that realm, it is quantum mechanics that holds sway. Us realm mein, which is the realm of the microscopic world. In this realm, it is quantum mechanics that holds sway. इस realm में, इस microscopic world में quantum mechanics की हुक्मरानी है. क्लासिकल मैकेनिक्स यहाँ कदम नहीं रख सकती. तो आमतौर पर जब हम माइक्रोस्कोपिक ऑब्जेक्ट्स की बात करें, और माइक्रोस्कोपिक ऑब्जेक्ट्स से मुराद बैक्टीरिया भी अब आजकल के दौर में हो सकता है, लेकिन माइक्रोस्कोपिक ऑब्जेक्ट्स, a few electrons, a few protons, a few photons, a few neutrons. In that realm, it is quantum mechanics that dictates the operation of events. But there are certain macroscopic phenomena. There are certain macroscopic phenomena, large scale phenomena, which are also explained by quantum mechanics. और वो phenomenon मिसाल के तौर पर आप सब वाकिफ हैं, magnetism. All of you know what magnetism is. Iron filings are attracted to a magnet. You have permanent magnets. You have soft magnets. You have hard magnets. Now magnetism can only be explained by quantum mechanics. So magnetism is a macroscopic phenomenon. A magnet can be the size of this keyboard. So it's a large object. A laser. Lasers can be very large objects. Lasers can be very large objects. You can have a laser the size of the SSE complex. So these are macroscopic objects. You use lasers to find the distance from the earth to the moon. You use lasers for lidar. You use lasers for for laser therapy, photodynamic therapy. You use lasers for shaping your cornea and so on. So lasers are really macroscopic objects. Then you have superconductors. What is a superconductor? Does anyone have an idea of what a superconductor is? क्या होता है superconductor? Zero resistance material. ऐसे भी material exist करते हैं जिनकी वाकई resistance zero होती है. हम ये कहते हैं कि copper की negligible resistance है, इसीलिए हम copper की connecting wires इस्तेमाल करते हैं, या सिल्वर की कनेक्टिंग वायर्स इस्तेमाल करते हैं, या गोल्ड के इंटरकनेक्ट्स इस्तेमाल करते हैं अपने माइक्रो इलेक्ट्रॉनिक सर्किट्स में. लेकिन हम एज्यूम करते हैं कि रेजिस्टेंस इज जीरो, बट द रेजिस्टेंस इज नेवर जीरो. देयर इज ऑलवेज अ फाइनाइट रेजिडुअल रेजिस्टेंस फॉर दीज मटेरियल्स, बट देयर आर सर्टेन मटेरियल्स फॉर व्हिच द रेजिस्टेंस इज precisely equal to zero, and these materials are called superconductors. And these are very important materials because they are used in, for example, MRI, magnetic resonance imaging, for producing these very large magnetic fields. We have these superconducting trains. So how does a superconductor work? We know that every material has a certain viscosity. आप पानी लें, उसकी एक viscosity है. जब आपने फ्रेशमैन लैब में एक एक्सपेरिमेंट किया, यू हैड अ हार्मोनिक ऑसिलेटर, अ बॉब दैट वाज ऑसिलेटिंग, यू पुट इट इनसाइड वाटर, यू सॉ द डैम्पिंग ऑफ द कर्व ऑफ अ सिंपल हार्मोनिक मोशन, व्हिच मींस दैट वाटर हैज अ सर्टेन विस्कोसिटी. यू परफॉर्म द एक्सपेरिमेंट इनसाइड एयर, स्टिल यू ऑब्जर्व द डैम्पिंग, व्हिच मींस दैट एयर हैज अ सर्टेन विस्कोसिटी. So every material has a viscosity, but you can think of a fluid that has zero viscosity, that flows without a potential drop, and such a material is called a superviscous material or a superfluid. A superfluid. So how do you explain superfluidity? You need non-classical concepts, and there's a huge plethora of large number of phenomena that can only be explained through non-classical physics. तो non-classical physics से हमारा वास्ता रहेगा इस कोर्स में, और ये थोड़ी सी काउंटर इंटुइटिव है. हमारी परवरिश जब हुई, ये बायोलॉजिकल ऑर्गेनिजम्स, ठीक है, वी आर सब्जेक्ट टू द लॉज ऑफ एवोल्यूशन. आवर अपब्रिंगिंग एज ह्यूमन बीइंग्स and the upbringing of this civilization, of the human civilization, has been within a biological context, and we only need the rules of the game that are relevant to us. We wanted to make automobiles, we only need a power source, we need chemical engineering, we need batteries, and we need the laws of mechanics. We did not require any quantum mechanics in our growth as a civilization up till the 20th century. We wanted to plant seeds and harvest the fruit of our agricultural toil. We did not need any quantum mechanics for this. But in the 20th century, there were certain realms which the civilization entered. And those realms required a newer understanding of nature. And that is what quantum mechanics is about. And so it's a bit counterintuitive. Because our upbringing as human beings, we are almost, most of you would be, I would say 18, 19, 20 years old. You have about, I think, 12 years of education. We have not come across quantum mechanics because we did not require it. But now, when we are to become scientists and engineers, we have to enter new realms. We have to explore new frontiers. And those frontiers require us a deeper understanding of nature's way. And quantum mechanics is really nature's way. So most of the concepts that we will learn will look a bit counterintuitive. Counterintuitive समझते हैं? क्या मतलब counterintuitive का? थोड़े से हैरान कौन, थोड़े से surprising. We will be shocked by these new concepts. That is why Niels Bohr का नाम सुना होगा आपने? That's why Niels Bohr said that anyone who is not shocked by quantum mechanics has not understood it. Anyone who is not shocked by quantum mechanics has not understood it. So we really have to enjoy this element of surprise. We have to be shocked because all of these concepts are counterintuitive. Counterintuitive का मतलब intuition होती है इंसान की एक intuition जो वो लेके पैदा होता है, जो परवरिश होती है उसकी. For example, we know that there are 3 dimensions or 4 dimensions. It's an intuitive concept. पुराने ज़माने में जब किसी जानवर का शिकार करने की ज़रूरत पड़ी 3000 साल पहले, तो जो शिकारी था, he had to throw an arrow, he had to throw a projectile, he had to throw it in the 3 dimensions of space and the 1 dimension of time. He had to look at the angle, the orientation, and the speed. So he was only concerned with 4 dimensions, the 3 dimensions of space and the 4 dimensions of time. That is how our wire is, how our brain is wired. हमारा दिमाग, हमारा ज़हन इस तरह इवॉल्व हुआ है. तो हमें 11 dimensions का कॉन्सेप्ट समझ नहीं आएगा, because it's counterintuitive. But in order to explain the fabric of the universe, in order to explain string theory or the unification of relativity and quantum mechanics, we need 11 dimensions. So it's a counterintuitive concept. तो हम सिर्फ उस पे हैरान हो सकते हैं, लेकिन हमारी मैथमेटिक्स के नतीजे में वो 11 डायमेंशंस निकलती हैं. ठीक है. फिर चूंकि हमारी परवरिश ऐसे हुई है कि हम 3 डायमेंशंस ही हमें नजर आते हैं, सवाल ये पूछा जाता है बाकी डायमेंशंस कहाँ गई, बाकी की 7 डायमेंशंस कहाँ गई. देन देयर आर एक्सप्लेनेशंस ऑफ वेयर दोस 7 डायमेंशंस हैव गॉन. दे हैव बीन कॉम्पैक्टिफाइड, दे आर सो स्मॉल दैट वी कैन नॉट सी देम. And you need to do very high energy experiments to expose those extra 7 dimensions. You have to make an LHC, a multi-trillion-dollar experiment, and see if it works. So these are all counterintuitive concepts, and classical mechanics is very counterintuitive. So when the ideas of quantum mechanics were being given birth to at the beginning of the 20th century, 1800 के आखिर में, 1900s के शुरू में, प्लैंक और आइंस्टाइन अलग-अलग वक्तों में काम करते हुए, लेकिन एक दूसरे के काम से वो वाकिफ थे. जब वो क्वांटम मैकेनिक्स की बुनियादें रख रहे थे, तो उनके लिए भी ये काउंटर इंट्यूटिव था. हत्ता कि आइंस्टाइन ने 1930s में कह दिया था, इतना काउंटर इंट्यूटिव था कि वो खुद भी उसे यकीन नहीं आता था, और वो कहता था गॉड डज नॉट प्ले डाइस. इतने ये काउंटर इंट्यूटिव कॉन्सेप्ट्स हैं. लेकिन अब इस बात को 1 सदी गुजर गई, तो जो प्रैक्टिशनर्स हैं, प्रैक्टिशनर्स जो काम करते हैं क्वांटम मैकेनिक्स में या नॉन क्लासिकल फिजिक्स में, उनके लिए बातें काउंटर इंट्यूटिव नहीं रहती. लेकिन चूंकि ये आपका पहला एक्सपोजे है, आपका पहला तारुफ है इन कॉन्सेप्ट्स के साथ, इसलिए ये बातें आपको थोड़ा सा हैरान करेंगी. ये कोर्स आपको थोड़ा सा हैरान करेगा, और ये खुशी की बात है. और आप थोड़े से कंफ्यूज होंगे और पजल होंगे, लेकिन आप ये सवाल जरूर पूछेंगे